morning. Today we will study subbases and subspaces. First of all, subbases. A subbasis for a topology on X is a collection S of subsets of X whose union is equal to X. So the topology T generated by the subbasis S is defined to be the collection T of all unions of finite intersections of elements of S. Clearly, S is a subset of B and B is a subset of T. Now we have one lemma which states that let S be a subbasis on X. The associated collection B is a basis for a topology. So we need to prove that the collection B is a basis for this topology T. So for this we will prove it in two steps. First of all, number one, suppose X belongs to capital X. So this lies in some element S of S, where S is a collection of subsets of X. Hence this is an element of basis element B, which is equal to S, where S is an element of B. Number two, suppose B1 is equal to S1 intersection S2 intersection Sn and B2 is equal to Sn plus 1 intersection Sn plus 2 intersection dash 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 up to Sn plus m. Suppose B1 and B2 are basis elements and X belongs to B1 intersection B2. It means X belongs to B1 as well as B2. Suppose B3 is the intersection of B1 and B2. It means it is the intersection of S1 intersection S2 intersection up to Sn intersection Sn plus 1 intersection up to Sn plus m. Means B1 intersection B2 is S1 intersection dash 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 intersection S m plus n. It means B3 is a basis element and X belongs to B3 because B3 is the intersection of B1 and B2. Now subspaces. Let X3 be a topological space and A is a subset of X. Then the collection TA, which is equal to A intersection U, where U is the element of T, then this collection TA of subsets of A is called the subspace topology on A. With this topology, ATA is called a subspace of X. Now we have one more lemma. The collection TA is a topology on A. To prove that TA is a topology on A, we will prove all the three conditions which are satisfied for being a topology. Number one, phi, we can write phi as A intersection phi, and we can write A as A intersection X. So these are the element of this form where TA is equal to A intersection U, where U is the element of T. Here phi is the element of T and X is the element of T, and we can write phi equal to A intersection phi and we can write A equal to A intersection X. It means phi and A are in TA. Number two, each subcollection of TA can be indexed as A intersection U alpha, where alpha belongs to J. For some subcollection U alpha, alpha belonging to J of T. It means union of alpha belonging to J, A intersection U alpha can be written as A intersection union alpha belonging to J U alpha by the distributive law. It was union of alpha belonging to J, A intersection U alpha. This is equal to A intersection union U alpha, where this union of U alpha, alpha belonging to J is in T. Because this is in T, therefore this total element is in TA. It means this union is in TA. Number 3, each finite subcollection of TA can be indexed as A intersection U1 dash 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 A intersection UN for some finite subcollection U1, U2, UN of T. It means A intersection U1 intersection dash 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 intersection A intersection UN can be written as A intersection U1 intersection dash 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 intersection UN. This is again by distributive law. And U1 intersection dash 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 intersection UN is in T. Hence, this intersection is in TA. It means all the three properties are satisfied and the collection TA is a topology on A. When ATA is a subspace of XT and V is a subset of A, where A is a subset of X, there are two possible meanings of the assertion V is open. Namely, V belongs to T or V belongs to TA. In general, these two meanings are different. If we say that V is open in X or that V is open subset of X, it means V belongs to T. If we say V is open in A or V is an open subset of X, it means V belongs to TA. And this later assertion means that V is equal to A intersection U for some U which is open in X. We have one more lemma. If B is a basis for topology T on X and A is a subset of X, then the collection BA, where BA is equal to A intersection B and B belongs to B, is a basis for subspace topology TA on A. Now we want to prove that BA is a basis. Each subset A intersection B in BA is open in A. Since each basis element B belong to B is open in X. Further, each open subset of A has the form A intersection U for some open subset U of X. If X belongs to A intersection U is any point, it means X belongs to U. So, since B is a basis for topology T, there exists a B belonging to B with X belonging to B and B where B is a subset of U. It means A intersection B belongs to BA by definition, and X belongs to A intersection B, and A intersection B is a subset of A intersection U. Therefore, by lemma, BA is a basis for the topology TA. We have an example. Suppose X is equal to R is the standard topology generated by the open interval AB. Let A is equal to 0, 1 means it is closed at 0 and open at 1. The subspace topology on A has a basis consisting of intersections means 0, 1 intersection AB. Here AB is the open interval, 0, 1 it is closed at 0 and open at 1. That is the subset of 0B and AB where B is less than 1. 0 is less than A, is less than B, and B is less than or equal to 1 because this is open at 1. For instance, if we write 0 to half, it is closed at 0 and open at half. It means we can write it as 0, 1 intersection minus half to half. This is an open interval and this is closed at 0 and open at 1. So we can write semi-closed interval 0 half as 0 to 1 intersection minus half to half, And we can write 0 to half, this is open interval, to be 0 to 1 intersection 0 to half. It is open interval, it is closed at 0 and open at 1. These are both open subsets of 0, 1 in the subspace topology. Now one more example, let Xt be a metric space with basis B equal to BDX epsilon, means it is a ball centered at x and radius epsilon, where x belongs to x and epsilon is greater than 0. For the metric topology, T equal to TD. Here BD x epsilon is the collection of y belonging to x such that distance of x from y is less than epsilon. Let A is a subset of x. Suppose A is any subset with metric dA equal to dA cross A given by dAxy equal to dxy for all xy belonging to A. The metric space ADA has basis B dash which is equal to BDA x epsilon, where x belongs to A and epsilon is greater than 0 for the metric topology. It means T dash is equal to TA dash, where TDA is where BDA x epsilon is equal to y belonging to A such that distance of A from xy is less than epsilon. This is a ball centered at x and radius epsilon. So it is the collection of all the elements of A such that whose distance from x is less than epsilon. It means B dA x epsilon is equal to A intersection BD x epsilon for all x belonging to A. It means B dash is subset of BA and T dash is a subset of TA, where TA is a subspace topology on X. To prove that the two topologies are equal so that TA equal to T dash, we use the lemma to check TA is a subset of T dash. Thus, consider any basis A intersection BD x epsilon in TA and any other element y belonging to A intersection BD x epsilon. It means delta is equal to epsilon minus dxy is positive and BDA y delta is a basis element in B dash. Y belongs to BDA y delta and BDA y delta is a subset of A intersection BD x epsilon. Now open subspace. By an open subspace of X, we mean an open subset A of X with the subspace topology. We have one more lemma. Let A be any open subspace of X. Then a subset V of A is open in A if and only if it is open in X. Suppose first that V is open in A in subspace topology. It means V is equal to A intersection U for some U that is open in X. Since A is open in X, it means that the intersection V equal to A intersection U is open in X. And conversely, suppose V is a subset of A is open in X. It means V is equal to A intersection V, so V is also open in A. So we have proved that subset V is open in A if and only if it is open in X. We have one more lemma. Let X and Y be two topological spaces with subspaces A and B respectively. Then the product topology A cross B is the same as the subspace topology on A cross B as a subset of X cross Y. So the subspace topology on A is generated by the basis with elements A intersection U, where U ranges over all the open subsets of X. This we have seen in last slides. Likewise, subspace topology on B is generated by the intersection B intersection V, where V ranges over all the open subsets of V. It means the product topology A cross B is generated by the basis with elements A intersection U and cross B intersection V, where U and V ranges over open subsets of X and Y respectively. On the other hand, the collection of products U cross V is a basis for the product on X cross Y. So the collection of intersections A cross B intersection U cross B is a basis for the subspace topology on A cross B, where U and V are still range over open subsets of X and Y. So A intersection U intersection B intersection V can be written as A cross B intersection U cross V. These two bases are in fact equal, hence they generate the same topology. Suppose we write A is equal to S1, which is a subset of two-dimensional real space, and B is equal to 0 to closed interval 0 to 2 pi, which is a subset of R. Then the product of A cross B is equal to S cross 0 to 2 pi, and this is because this is subset of R square, this is subset of R, so this is equivalent to R cube, and is A cross B is a cylinder. If we view R as R cross uh, product of singleton set 0, which is a subset of R square, there is a room to bend in the interval B, which is equivalent to 0 to 2 pi cross 0, which is a subset of R square, to bring its ends closer together, eventually forming a loop B dash equal to S1, which is a subset of R square. The product space A cross B dash is equal to S1 cross S1 is a subset of R square cross R square, and this is equivalent to R4, and it is obtained from the cylinder S1 cross 0 to 2 pi by bringing the two ends and circle together. This can be realized with an R cube by the torus surface. Hence, S1 cross X1 is topologically the same as the torus surface. Thank you.